I'm Anil Kumar. This video is for my students who graduated from school thinking calculus is not important for them as they're taking economics or marketing in the university. I find them coming back again and again to understand some concepts. So this video is for those students who really didn't take seriously calculus at school. So I'll try to explain the concept at length. At times it could be boring for some smart kids. Anyway, you may skip the video. So we'll talk about optimization by Lagrange's method. So we'll talk about some basic concepts followed by an example. The example which I'm going to take is this one, which is find extreme value of the function fxy equals to x squared plus 2y squared on the circle x squared plus y squared equals to 1. This equation represents an ellipse. Okay, so let's try to understand the concepts first, move on, and then see how to solve questions based on this topic. I will take many more examples in the following videos, so if you need more practice, you should check the links provided. Okay, so we're talking about optimization. That basically means we're looking for something which gives us maximum value or minimum value, right? We have to maximize the profits, minimize the cost kind of things, right? So you have many applications based on this. Lagrange's method is very helpful in solving such when we are dealing with multivariables. Multivariables, right? So it is indeed a step above you ever learn in school. So it's a good bridging between the two levels. So multivariables, let me take a general function first to explain what I'm trying to say. So let's say the general function is f, x, y, and z, right? So when I say x, y, z, that means there are three variables which we have to work with, and optimization, as you know, we always have some constraints. So for this general function, we say let this be equals to c, and we'll talk with help of a constraint. Constraint means a boundary condition, right? So a constraint could be, let's call this function as we normally use in our books as g of x, y, z equals to k, right? So that becomes a constraint. For example, if you're checking the maximum, if you have to maximize the volume, the surface area is given to you as a constraint, right? At times cost could be your constraint. So it's kind of like this. So that's what we'll work with and try to understand. To begin with, let's take two variables. Instead of three variables, it could be complicated. So let me take two variable case just to explain you the concept better, right? So we'll take two variables. So when I say two variables, what does it mean? It really means that the general function now becomes f of x, y. These are two variables equals to constant, and the constraint becomes g of x, y equals to k. Does it make sense to you, right? So these are two variables. Now, when you say f of x, y equals to c, that means c could have different values, correct? So c could be 1, 2, 3, 4. Let's take any value, right? So we're talking about real numbers in this particular case. So general case means, let me show you two dimensions. So these are my two dimensions. So I'm saying that x is along the x-axis as we normally see, right? X, and this is y. So if I have to draw this function for different values of c, I could always sketch this function as, let me take another ink here. So let's say the function is kind of like this, right? So this is kind of a function, right? So okay, so this is different values of c, right? So this is kind of a function here. So as we increase the value of c, let's say that the function is kind of like this. So this is my function for different values of c. So let's say if c is equals to 1, this is the curve. If c equals to 2, that is the curve. For 3, this is the curve. 4 and 5, kind of like this, right? So that is my function f of xy equals to c for different values of c. When we say constraint on the function, that means we're only considering the points. So what does this constraint means? Let me highlight this portion, constraint. So when I say constraint, it means that you have to follow the points. So only points on g of xy will be considered, right? Not all these points. So when we say that the general function is under the constraint and we need to maximize it, so we're looking for points on g of xy. So let me sketch the function g of xy also, and then we'll talk further about it, okay? So let's say the function g of xy is kind of like this. Okay, let's say this is tangent, right? This is common point. So this is my function, which I'm saying is g of xy. So when we say only points on g of xy, that means we are really interested in these points. Do you see? Common to both. I mean, this is one big point, very important for me. So these are the points which we are considering, right? Now from this diagram, it makes good sense that the common point with maximum is right there, right? So what we have is that as our solution. Is it okay? So if you could draw, which is very difficult at times, you could write down that to be your solution, right? Because when we are considering the function fxy, where the constraint is gxy, which is this curve, maximum value you get here. Perfect. Now what is important to understand here is that all these points, the slope on the curve for g of x is shown in green, for example, right? And let's say for f of x, I'm showing slope in red. Okay, so this is the slope in red. Okay, but at this position, you find that the slopes are same. So what we notice here is that at, let me use the word extrema here. In this case, it happens to be a maximum. In this case, a max point. So what we notice that at extrema, gradient is same for the function fxy, which we're considering, and gxy, right? So at this point, let's call this point as x0, y0, correct? So that means that f x0, y0 will result in a maximum in this case, right? So it results in a maximum in this case. So what you learn here is that the slope or the gradient is same, right? So that gives you that the normal will also be same, right? Normal will be equal at extrema. So that is the basic concept. So what we have learned here is that the gradient is same, normal is same, right? So same here means parallel. Parallel, if you have to equate it, we will use scalar multiple, right, as in vectors. So what we could write here is that the gradient for the function fx, since I'm taking this point as x0, y0, is equals to the gradient for the function g x0, y0. To make them equal, we'll have a multiplier, a scalar multiplier, lambda, right? So this lambda is actually called Lagrange's multiplier. So if you correlate with what you've learned in vectors, it is a scalar multiplier, right? Lambda. So that's what it is. So let's get back to this once again. So what we have here is a function in two variables, fxy equals to c. with a constraint gxy equals to k. That means on this function, we are only interested in the points which are on g xy equals to k. So this sketch shows us that for different values of c, we could have these curves shown in orange. And this curve shown here is gxy equals to k. From their point of intersections, we know the points in which we are interested. And definitely, the point P, which is marked here as x0, y0, is the one which gives us the extreme value. At this point P, what we notice is f of x0, y0 will result in a maximum, and you also notice that normal will be equal at maxima for both curves, right? So both f and g functions. Do you see that? Both are equal. And therefore, we can write that the gradient at f of x0, y0 is equal to scalar multiple lambda, which is called Lagrange's multiplier, times the gradient for the constraint, right? So this becomes our method of solving or answering the optimization cases. I hope you get the concept here, right? Now with this in mind, we'll further explore the three-dimensional. So if the case is for three-dimensional, we're talking about a function x, y, z equals to c, and the constraint is g of x, y, z equals to k. And in that case, the conditions will be same, right? So it will be again the gradient of this function and x0, y0. z0 has to be lambda times the gradient for x0, y0, z0, right? So this could be extended to three dimensions with the same reasoning, correct? So that is how we are going to solve. So now let's take up the example and continue, rather understand it better with the help of our example. I hope the basic concept is absolutely clear. Now let's take this example, which is find extreme value of the function fxy equals to x squared plus 2y squared on the circle x squared plus y squared equals to 1. So in this case, what is the function for us? Let's write down the function. So the function for us is f of xy equals to x squared plus 2y squared, right? That's the function. So as I explained earlier, we'll actually sketch the function x squared plus 2y squared equals to c, right? We'll sketch this function. So I'll follow exactly the same principle which we did just now, basic concepts, and then find a solution. So we'll do a solution using a sketch first, and then we'll do the same with algebraically, okay? So the function itself, which I'll draw in orange, not so good, will be an ellipse, right? So let's select this. Okay. So this is, let's say, when the value of c is 1, and then we could do it like this when the value of c is 2. Okay. We could do like this when the value of c is 3, for example. Okay. So this gives you a fairly good idea of what we are trying to do. So what I've drawn here is you can say this is x squared plus 2y squared equals to 3, this curve, right? This could be x squared plus y squared equals to 2, and this could be, I should have written so, okay, it doesn't matter, x squared plus 2y squared, 2y squared equals to 1, right? So this is like 1. I should not write 1 here anyway. It doesn't matter, okay. So if x is 1, the value of x squared plus 2y squared is 1, okay. C is 1, that's what I'm trying to say. So these are for 3 different values of c. Now what we have here is a constraint. So what is the constraint for us? Let's write down. So constraint which we normally write with g, so g of xy is what? Is x squared plus y squared equals to 1, correct? That means we are interested in all the points of the function which take these xy values, correct? Now this is a circle, correct? So what you notice here is that this is an ellipse and this is a circle. So this circle you could draw kind of like this. So that becomes the circle representing the constraints. So this green part is the circle. Okay. Now what do you notice here? You notice that we have a common point right there and right there. These are the two common points which gives you extreme values, correct? These gives you extreme values. Also, we have these common points. So at these points, we have the same gradient. You get an idea, right? So at these points, we get the same gradient, correct? So those are our extreme points. So those are the values which belong to the solution of the problem. We just find the extreme values. At these points, the normals to the curve of the function and the constraint are parallel, correct? Or you can say that they are scalar multiple. Do you get an idea? Correct? So what we're trying to say here, that at these points, f of x is equal to lambda times g of x, and f of y is equals to lambda times g of y, correct? Do you get an idea, right? Where g of xy is equal to 1, correct? So that is what it is. So from this, you can do the partial derivatives. So let's do the partial derivatives. So when you do partial derivatives, then for the function, you get 2x equals to lambda times, and for the constraint, you get 2x, right? 2x. For y, you get 4y equals to lambda times where is this? 2y, lambda times 2y. Is that okay? So that is what you get. And the equation which you have here is x squared plus y squared equals to 1. So that is the constraint given to you. Is that okay? So that is how you could actually solve this question algebraically, correct? And now from here, what values of x can satisfy? We know lambda is not equal to 0, correct? Lambda cannot be placed as 0. So from the first equation, which is this one, we can say this is always true if x is equals to 0, right? So this is the solution. So that is the solution for us. Is that okay? X is equals to 0 becomes the solution for this, correct? So if I write x as equals to 0, then what do we get? The value of y. What do we get? The value of y. So in this equation, if I substitute x squared plus y squared equals to 1 with x equals to 0, I get y equals to, let's say 0 equals to y squared equals to 1, implies that y equals to plus minus 1. Is it okay? So for this particular condition, we get, let me just push this a bit. So for this particular condition, we get 2 points which are for x equals to 0, y is plus minus 1. Do you get an idea? Is it okay? Similarly, we can do for the second condition, which is here. We have y equals to 0 now, right? So if y is equals to 0 is the solution, then what is the value of x? X is equals to plus minus 1. If I substitute in this equation, is that okay? So that means that the solution is plus minus 1, 0. So those are the 2 points. So these are these 2 points. Do you get an idea? Plus 1, minus 1, y is 0. And those points which we're talking about, let me circle them on a different ink. 0 and plus minus 1 are these 2 points. So these are the 4 points which we are considering. Do you get an idea, right? Now, so these are the points. To find what leads to maximum, what leads to minimum, we need to evaluate f of xy for critical points or critical numbers. Do you get an idea, right? So that is how we proceed. I hope the concept is getting along clearly. So for the first case, if I write f of 0 plus minus 1, for example, in that case, if I substitute 0 plus minus 1, I get 0 plus 2 times plus minus 1 whole square. That gives me a value of 2. If I substitute plus minus 1 and 0, the other set of points, in that case, I get plus minus 1 whole square plus 2 times 0, which is 1. Correct? Which is 1. So from here, we know that the maximum occurs at this point, 0 plus minus 1, where the result is 2. So this gives you maximum value. And that gives you a lower value, the minimum value. Do you see that? So that gives you the minimum value. So the maximum value and the minimum values can be found from the example, right? In this fashion. So that gives you the minimum value of the function where the normals are as shown here. So this is a surface. Don't treat it as xy. So on this particular surface, what we find is that the maximum is at f of 0 plus minus 1 and minimum is at f of plus minus 1, 0. Do you see that? And the values are 2 and 1 respectively. So that is how we could actually algebraically solve the given question. But I hope this concept from where we really started is absolutely clear. What you notice at these points where you have extrema, the normals are parallel. So what do we take from here is that the normals are parallel at extrema for function and constraint. Let me write g of x0, y0. Is it okay? So that is what we understand. And based on this understanding, now we'll have more examples to practice. I hope that makes sense to you. Feel free to write your comments, share your views and your questions. Thank you and all the best.